Hi guys, this video is by my teen kids. Now these kids have really put in their effort in making this video on catalysis. Hope you enjoy the video.
We would be dealing with these catalysts. Hello guys, I am Komal. So firstly, light, which is represented by HNO. We have UV light giving a chiral product and circularly polarized light giving chiral product.
Around 1930, Michel and Kuhn had done kinetic resolution of racemic mixture via circularly polarized light, which Komal mentioned right now. Alright, in that case, what they did is they enantioselectively destructed one of the isomer, like in this case it is the positive or the S isomer, which was decomposed, and what remained behind was negative or R enantiomer of A. Now this was one of the greatest achievement, because from this it was proved that circularly polarized light could enantioselectively destruct one of the isomer. Right? Komal also mentioned about achiral synthesis using UV light. Alright, now in this case, during my synthesis of 6 ppd, I had got a byproduct which was an amide, rather which was a formamide. Alright, now this formamide I tried to hydrolyze using UV light, giving acid and amine. But in this case, what I observed that I got 15% success, around 10 to 15% success I got. Alright, though it was an achievement, but not worth publishing. Alright, so UV light also can be used for achiral synthesis.
Moving on to metals, we have ranitidine, palladium with charcoal, which my colleague Ankur is going to represent, giving a chiral product, and chiral ligand metal complex giving chiral product. Moving on to enzymes, it gives both a chiral product and chiral product, where some immobilized enzymes are reduce-selective, giving a chiral product, and normal enzymes are enantioselective, which give chiral product.
Thanks, Komal. Hello everyone, myself Srihari, and today we'll be dealing with Noyer's asymmetric hydrogenation. So Noyer's asymmetric hydrogenation refers to the methodology for enantioselective reduction of ketones as well as related functional groups. So this methodology was introduced by Noyer, who was honored by a Nobel Prize in the year 2001. So let us now understand prochirality in depth. So this carbon present over here is prochiral, so sp2 hybridized. As we all know that sp2 hybridized are planar in structure. So the nucleophile can attack from D or C, giving you two different enantiomers. So proceeding to the reaction, we are having ethyl 3-oxobutanoate. This carbon is prochiral. So what are prochiral? Prochiral carbon compounds are the compounds which can be converted into chiral compounds in a single step. So let us try and understand enantioselectivity of chiral organophosphorus catalyst, where BINAP is chiral ligand which prevents formation of racemic mixture. So as I mentioned, it is the isomers of BINAP, that is R or S, which decides the enantioselectivity of the product. So when the substrate ethyl 3-oxobutanoate is reacted with ruthenium R BINAP, we get corresponding S alcohol where OH is present above the plane, as given in the figure. And similarly, if we treat the ethyl 3-oxobutanoate with ruthenium S BINAP, we get corresponding R alcohol where OH is present below the plane.
This is the structure of 3-oxo ethyl butyrate. Now let's analyze why is it, first of all, derivative of butyric acid. Now it is derivative of butyric acid because we know that this carbon 1, 2, 3, 4. This is 4 carbon acid. Now this is C double bond O, this is C double bond O and O, and C2H5, C2H5, CH3, CH2. So this is ethyl group, O, C double bond O. So this is the ester part, and the backbone is of that of butyric acid, 1, 2, 3, 4. And in third position, first, second, third, in third position there is a ketone group. So we call it as 3-oxo ethyl butyrate. Alright, so this is what is the structure of ethyl butyrate. Now what we are interested in is this carbonyl. Now this carbonyl is prochiral. Now why prochiral? Because this carbon is in sp2 hybridized state. sp2 hybridized state means planar structure. You can say it's a planar structure, right? C double bond O attached here. This is another CH3 and this here another C. Now this is in one plane. So nucleophile can attack from here as well as from here. So as Hari explained, re-C attack. Alright. So if nucleophile attacks from here, so it gets attached on the top, we get one optical isomer. And if the nucleophile attacks from the base, we get other isomer. Alright. So that's the reason why this is called as prochiral. Either you attack nucleophile from here or nucleophile from here, you would get a chiral compound. Now why chiral compound? Now suppose in our case what we are going to do is we are going to get one OH over here and H over here. Alright. So it would have 4 different groups attached. Now here we would have OH, there we would have H, and this is CH3 and this is the other group. So this would be a chiral center. Alright, let's understand with model further. Alright. So this is the isomer that I have got. Now see, this carbon has become chiral. Why? Because now if you check out this group and if you compare with this group and if you see this group and if you see this, all 4 groups attached to this carbon are different. So this becomes the chiral center. That's the reason why we call ketone C double bond O, which was there earlier over here, we call that as prochiral. Why? Because on reduction it gave, on just single step reduction, it gave a chiral molecule. Now that's not all. Now since we have used a ligand which is chiral in metal complex, so we have got this isomer where OH is at the top. Now if I use the counter isomer, the other isomer of ligand in chiral catalyst, then this OH would be down. Let me try to show. That's a mirror image, right? So let me try to show how it would be. Now see, this same thing would be going down like this. So this is the molecule. This is now, this OH is down there. Alright, now so OH here now is down. So this is the other isomer that Hari explained, right? So it all depends upon chiral ligand that we are using for enantiomer selectivity.
So this compound is intermediate for several drugs, for example, antibacterial levofloxacin. So now my colleague Mayuresh will explain further.
Thanks Riyari. So today I will be explaining KB Sharpless asymmetric epoxidation reaction. Hi, I am Mayuresh. In this reaction, prochiral alkene is converted into 2,3-chiral epoxide in the presence of chiral catalyst DET, that is RR diethyl tartrate, and T titanium tetra isopropoxide in the presence of oxidizing agent tert butyl hydroperoxide. If we don't use this chiral catalyst, we end up with racemic mixture. If we use RR diethyl tartrate catalyst, we get this enantiomer, and if we use SS diethyl tartrate catalyst, we end up with this enantiomer. So we conclude that single enantiomer is obtained because of chiral catalyst. Now my colleague Harsh will explain the further part.
Let's understand the structure that Mayuresh used for Sharpless epoxidation. Now this is an allylic hydroxide. Now why is it allyl? Because whenever there's double bond to beta carbon, and why is this beta carbon? Because hydroxy is attached over here, so this becomes alpha carbon, and double bond is there at the second one, that is beta carbon, so we call it as allylic or allyl alcohol. Alright, now that's about allyl alcohol. Now understand the molecule. Now if we observe this carbon, this has got this group attached here, that is CH2OH group attached here. If we observe this carbon, if we attach this group, this is the ethyl group which is attached here, and then if we come to this carbon, to this carbon we have got propyl group attached over here, and again to this carbon, if we see, we have got here methyl group attached. All right, so this is methyl, propyl, ethyl and CH2OH. Alright, so now we are to do epoxidation of this double bond. Let's see how it appears. Now all the things that I explained earlier that is chiral catalyst that we are using. It is highly enantioselective, and this also becomes prochiral, because if you check out this carbon, you will find that this also has a planar structure, right? It is plane over here. This also has a planar structure. So this is so epoxidation, oxygen can come like that, or it can come like that. So as a result of which, it can give you two optical isomers. All right, let's see how the epoxidation occurs. But of course, this all happens provided we are using chiral catalyst as we have used. All right. So guys, we have got to focus into this double bond. All right. So let's understand how the reaction occurs. All right. We would find that one bond would remain there and another epoxide would come on top of it. All right. Okay guys, this is the structure, that molecular model that we have got on epoxidation. So this is the epoxide which has formed, newly formed. All right, now let's check out this carbon. Now if you check out this carbon, it has got this hydrogen over here, it has got oxygen attached over here, and this is one bond and the other bond is this. So what we find is the four groups attached to this carbon are different. Now since that they are different, so this carbon becomes a chiral carbon. Similarly, when we observe over here, we find the same thing over here. It has got oxygen attached over here, this has got carbon, and this has got this propyl group attached here and methyl group. So four groups attached to this carbon are different, so this also becomes a chiral center also. All right, so this molecule is now a chiral molecule. Now is it an optical isomer? Yes, it is. Why? Because we have got this OH, we have got this epoxide which is at the top. All right, so what would be the other isomer? The other isomer would have epoxide at the base, that is the mirror image. All right, I would try to make it, but prior to making it, let me also make you aware that this enantiomer was possible only because we used chiral catalyst. All right, in case of other isomer, it would be the mirror image. So if I say mirror image, then it would be like this. All right, the epoxide which is there would be at the towards the base, or rather the epoxide would be down there. All right, whereas in the other case, the isomer was like this, which was at the top. The epoxide was at the top, and the mirror, in case of mirror image, the epoxide would be at the bottom, like this.
Hi guys, myself Harsh, and today I am going to introduce an interesting topic, that is active sites. What do you mean by active sites? A specific region in catalyst where the reaction occurs is active. Out of these two substrates, which one will fit into this active site of this catalyst? Obviously substrate 1. According to lock and key mechanism, substrate 2 will get rejected, and this substrate 1 will get into this active site, and this is said to be stereospecificity. This is catalyst plus substrate complex, where catalyst provide the desired activation energy to form the product, owing to which the shape of the substrate changes and it is not recognized by the active site, and it is thrown out as the product. And this is how the active site works.
Harsh right now mentioned about activation energy. Now activation energy is being provided by catalyst. Now here, in case of biocatalysis, activation energy, it's not an easy process. The molecule has got to enter into active site. Now as he mentioned, active site works as per lock and key mechanism. So whenever we are talking in terms of biocatalysis, enantioselectivity is also one of the most significant criteria. All right. Along with that, there are regioselectivity and other things also involved, like pH is involved and temperature is involved, and lots of many things are involved in case of biocatalysis. Now, biocatalysis I have already dealt with in my earlier videos. All right, so here what I'm talking is mainly about IPPD and 6-PPD, that is a chiral catalyst. It's not chiral. All right, so here in case of 6-PPD and IPPD, the activation energy found for transfer hydrogenation of hydrogen from IPA to ranitidine was found to be 59 kilojoules per mole. All right, in case of IPPD. Whereas in case of 6-ppd, obviously as I mentioned in my earlier video, it was 5% palladium on carbon with formic acid. So the transfer hydrogenation occurred from formic acid to palladium on carbon. Activation energy provided by palladium on carbon was 13.8 kilojoule per mole in case of 6-ppd.
So hi guys, myself Advait and I will be speaking on the topic activation energy. So what is activation energy? It is the barrier between reactant and product as shown in the figure. Reactant has to cross this barrier to form product. Catalysts provide with this activation energy to form product.
Advait, I am interfering again. Alright, Advait talked about activation energy. Now, I determined activation energy for IPPD and 6-ppd, which were published in those international journals and got lots of reputation internationally. Now, for this, active sites found for ranitidine was 0.015 mole per gram of catalyst, and in case of 5% palladium on charcoal, it was 0.08 mole per gram of catalyst. Alright. Hope you enjoyed the video. More to come. See you soon.